So let me start today's class. You might have noticed that link I have put in Moodle about the first recorded application of statistics in history. We don't say it's the first one ever happened, but it's the first one recorded. And if you go to the materials folder, in the lectures, you will see the second lecture file, Thucydides and averaging. And this is a file for your benefit, for those of you who have not clearly, which I expect are most of you, have not opened the link out of some curiosity. You can start reading the passage and I will be describing what happens. Thucydides is describing the Battle of Plateas. Let's say this is the castle of the enemy. And in that castle, it was a small part where the plaster was off. So they could, from that part here, they could see the bricks. There were bricks all over the place, but they could see the bricks in just that part. So the Plateans were, let's say, here. And this was the castle of the enemy. And these are the bricks. And the problem was they wanted to make a do. They wanted to break the castle of the enemy's lines. And in order to do that, they had to create ladders on which they would climb. So the idea would be, for example, that there would be a ladder here with just the right height. It was crucial to have the correct height if you think about it. If it's too short, then they wouldn't be able to jump. If it is too high, then the enemy could push the ladder and send it down. Right? So it was crucial to design the ladders to have the correct height. And what do we do that now? We have to correctly count the height. So what they tried to do was to estimate, well, maybe they did have some measurement tools of the time. In fact, the ancients were supposed to know enough trigonometry which would help them do that. But anyway, they had to measure this from some distance, not very far. And basically the idea was every one of the warriors would try to see how thick these bricks are, and they would make an estimation. But in order to make sure that their measurements are precise enough, they did not allow one person to do that, but in fact, they had a lot of people do that, and everybody was making their measurement. And the idea was that later they would be more reliable in their estimations as to what would happen. Now, if you look closely to the passage, especially this last paragraph, it is not exact. It's not exactly certain what was the method that they used, the statistical metric. We will assume it was the average. We will assume that the Greeks knew how to calculate the average. It's very likely. Maybe with a geometric method, because in algebra they were not that good. But right now, let us try now and simulate this situation. And you can all try along with me in your files. So the idea now is we will get one warrior at a time to try to measure the thickness of the bricks. Historians clearly know later what was the precise height. But let us simulate now and try to see what the Plateans were able to do. So at first, and that's the method you will be working with the tutorials I will be giving you. So the method we will apply now is a method that you will be using also in your assignment, in your the homework I give you. So right now, let's get one warrior. This is Nervias, and he came and he gave a measurement of 44.96 centimeters. Of course, they didn't have centimeters at the time, they had different units of measurement. But we're translating this now. And maybe you get somebody else. Pedro, that's Nervias. He found 44.96. What do you think is the height of the brick?
47.
Why not 44.96? Why not exactly what he measured?
No.
Let's get one more. F Marcos. By the way, as you will see, this stays red for a while, simulating the fact that not everybody takes the same time. Okay, some people are faster, some people are slower. Katerina, what would you say is the height of the bricks?
Based on this information,
it cannot be 44 nor 47.
Why not?
Because when we take all the measurements, we add them up and then we divide them by the count.
Which is called the average.
The average. So it cannot be none of them.
The question is if one measurement is good enough for the average, or two measurements are good enough for the average. Okay.
one measurement.
So this is an intuition I want to build here now with the process. As you will see from what we have right now, we might guess that this guy got almost 45 centimeters. This is 47 and a half. It might be somewhere around 46, but let us see what the others are calculating. Tichias, he's taking a long time. Maybe Tichias actually made a more reliable measurement. Actually he did, because I know the true value. But that's accidental actually. He might be useless, he might be wasting a lot of time and still not making a correct measurement. I made some of them up. But they are... Yeah.
We have difference here.
Yes, of course, because it's simulation. But if you run the whole thing now, get 5 warriors. Okay, we got a total of 10 right now. And let me reveal a trick. Select these cells here, J2 until K3, and give them a color. Make them automatic. So what we are seeing right now is the average of those who measured until now. And the average of these measurements is 45.75. And actually, historians told us that the correct value was 45.8. We can finish the experiment off by getting all the remaining warriors together. I have a total of 50 of them. Watch how the number is changing. And now we'll do this again, the same experiment again. Reset warriors. And now let us do it in steps. No, actually we'll do all remaining warriors together and watch out this number. As I said, this is the one that we know it's true. They didn't know at the time. They were trying to estimate. See now how this number will be changing as more and more warriors are coming and measuring.
We don't have that box.
What box? I said select these cells and make them black letter. So among other things, I will also need your concentration while I'm presenting. Get remaining warriors. Now we only made 50 of them, one after the other. What's the number? Sometimes it's getting closer, sometimes it's getting further.
It's getting closer.
Okay. Now, I believe I'm tapping on something that intuitively you all have as knowledge inside you, that when I rely on only one measurement of one person only, it was going to have some reliability, but clearly as I put more and more measurements and I'm averaging them, the extreme possibilities are off. Okay, we're going to work a lot on that later in the course. Right now, let us see a graphical representation of this. So notice how it's going to work here. Get one warrior. Now the warrior is going to come, measured, and now our chart is showing the following information. The green one is the true value as we know it later. Historians told us we cheated. This here is the average of everything measured so far. And the blue dot is the measurement of alkenos. Can we relate the position of the blue dot to the value over there? Where is it? Okay. The value is 46.04 and it is at 46.04.
Because it's only one.
Alright, because of the way it's plotted. It's one of the charts we learn how to make here. And because it's only one, the value of the one person is the average. In other words, if I believe that person, that first one and only warrior that I sent, then I would think that the bricks are 46.04. Okay, let us see how this picture might change with one more. One weak warrior. Huh. In fact, Sophocles, not accidentally, got a very correct measurement, got here, but at any rate, now, although the red was here, now it approached the green. Let's see if this will continue. We're running this several times. We're basically simulating a process. So Pisimorphos here found it on the high side. What was the effect of that? Look, the average moved there. That's something we're also going to work on and develop intuition in later lectures. But clearly the mass was here, and now I got some more mass in this direction, and that pushed the average in this direction. Get next warrior. Ha! And now we balanced this with somebody who measured on the low side. And the effect was that right now, the average that we have found from these four warriors is extremely close to the real. They didn't know that though. So they continued. Let's get remaining warriors and see how the red moves alive. Oh man, I have to fix this. I have to fix it. The red is not moving.
It's almost done.
No. No, it's not animating. It's not animating properly. It should be moving left and right with every move. I have to fix something this anyway. Reset warriors, get next 5 warriors. Something I need to fix with the animation here. It calculates, it evaluates very slowly. So basically the way we have to do it is I have to improve something. I don't know what, but you get the idea. So generally, when we simulate that properly, what we will see is that this red, initially with the first few measurements, might appear anywhere, but as more measurements are coming, this starts oscillating and eventually reaches the correct one, near the correct one. They still didn't know. So even though right now we can not see the red one moving with every turn, let us just complete the warriors, get remaining warriors, and let us see at the end of the experiment what will have been found. Yeah, it will only change in the end. Something will fix it. In my computer it worked properly. So, we're not finished yet. No, we are. When it says 50 here, we're finished. So 50? Yes.
Last question.
Yes, of course. Anything can happen, and we will study this too later. We will get formulas later for what's the probability that it's very close, for what's the probability that the final average, when I have 50 people counting here, when I have 20 people counting, when I have 100 people counting, what's the probability that it's so close or so far from the true average? Okay? A very similar experiment can now be seen in the next sheet, where, let's say, this is a total of 480 people. And let's say these are all the people in the ACT community, professors, students, exchange students, and everything. Right? And In fact, if you click in one of these cells, like I did here, you can see a number in the formula bar, but right now the cells are formatted to display only the question mark, although inside them they actually have a number. And what is this number? It's a body height of that person. Okay. So somehow we have all these body heights here. They are the population. That's a key term. Population. That's the population we are measuring. And let's say that an alien from another planet just arrived. Okay. And let us further say that this alien landed here on campus. And let us further say that this alien comes from a planet where everybody has the same body height. So we will now, when we click the button sample 1, we will more or less simulate that process of this alien encountering the first person that happens to be in front of his way. Who could that be?
Anyone.
Yeah, he knew where to go for... No, anyone. Right? Any one of these people could be the first person that the alien encounters. So it's this guy. Took some time to measure. 178.6. Now, if the alien comes from a planet where everybody has the same height, what will the alien conclude at this point? And how correct would he be? We don't know yet. He might be very correct, might be very wrong. He might have a high likelihood of being correct, or he might have a low likelihood of being correct the first time. Okay. Why it would be likely or less likely, there are also things we will gradually examine here. But at any rate, right now in my screen, the alien landed on this person first, and that person happened to be 178.6. This is the average known to the alien with the measurements until now. Pop average means population average.
The population average
Is we already know that. Yeah. If you click on the formula, it is average of all these cells. Okay. And somebody, God or our nurse, knows the height of everybody here, but the alien doesn't. This will never be changing. We have given the population, that's a population of 480 people. We know the average. The alien is trying to figure it out. Okay. So again, like with the Platees battle, we are cheating a little bit because we know. And we're trying to see how well is the alien performing in his effort to assess the body height of the humans. Now, next sample. And it's already enough for the alien to realize that this planet is different from his. That not all people have the same height. So in my case, this guy was brought up with 184.4. And now, since these are the two measurements, the average that the alien has in mind is 181.5. Okay. We can continue now, you can play a little bit. Sample 5. Right now it so happens that with the 7 people sampled in total, we actually got, our alien got a fairly good estimate to the real one, but he doesn't know that yet. Another 5. Maybe these next 5, we take him further. Actually they did. Before these last 5 ones, it was very close, 177.5. And now it went down to 177. So it so happened that these next 5 samples actually took him further from the truth. Another 5.
Who is 201?
These are imaginary here. I didn't take the measurements of everybody. But for example, we had a volleyball player here up until 2 semesters ago. He was
Alright. I should pay him.
No. Okay. Alright, so as you will see, if we sample all of them, it will take some time until everybody is revealed. And now you can see what was in there from the beginning.
This is sick.
This is what? Sick. Sick. But you sick or is it sick or the mind who made it is sick?
Mine.
Yeah, me, yeah, of course. Sickness is the mother of all invention, did you know? If I had chosen the color to be blue, it would be less the color. It's an interesting issue actually, it has to do with statistics. Somebody does something unusual. Will you call him sick?
No.
It's something we deal with in statistics. It's a concept of outlier. Okay. Somebody who is not in the norm.
He's not in the trend.
He's not in the trend. He's an outlier. And it's an issue when we will consider that to be somebody to be an outlier or not. And it has to do with a lot, with society itself, how society tolerates difference, and all sorts of stuff. For example, in ancient Egypt, they thought that the epileptics had they call them the disease of the gods. So essentially in ancient Egypt, an epileptic, rather than scaring people away by their culture, they thought that, here is a sacred person because he was blessed by the gods with this
In
disease.
Greece they said they were possessed by demons.
In later, not in Egypt.
Later, in the 18th century.
So the Egyptians think they are possessed by the gods. In the medieval ages, they thought they are possessed by the demons. Go figure. Right.
The average.
Demons makes
Because
no
they are.
sense.
Okay. All right. And let us actually now have a chart prepared here. So let us slide that chart up. And hopefully the animation will work better this time. Reset sample. And sample 1. Okay. So now the green bars here show the minimum, the shortest person of the campus. The shortest person is at 152.1. These are not real, okay? I can't. You will soon learn to do the same thing yourself. And so you can see the green bar here. It is at 152.1, the tallest, 201.5, and the average that we know. The alien doesn't know yet. And what is this now? The average that the alien thinks. Yes. In fact, since the alien is coming from a planet where everybody has the same height, the red shows his belief when he has only met one person. Okay. This belief is about to change because he will realize that this is not the case. Okay. And it so happened now, this time, it so happened that he happened to find two people with quite close. And so his estimation did not really change that much. Maybe in your screen something else is happening. Okay. Ooh, we're getting further and further. Can this happen? Yes. How frequently is another story. But it can happen. Further and further. And now finally somebody came here who pushed the average closer to the real. Things hopefully will improve when we sample a few more people. Another 5. In your individual screens, you might have the red already here. Could be, yeah, could be just behind. If you click one more, it might change position.
Here the line is moving.
So is it working now if I sample all these moving? Yeah, okay, great. If the patient has if the alien has the patience to measure everybody, needless to say, eventually, the alien is going to find the true average of this campus. But this campus is not all humanity. Okay, so again, the alien will have, once he samples everything, then the alien will know what is the exact average of this campus. Right? Yes?
But it's a good sample because there are people of different ethnicities.
Yes, it is a good sample. That's true. Or so we think. How you choose people, then again you might say, maybe here we have people who generally have higher income than the average, so maybe they got better nutrition, so maybe they tend to be slightly taller on the average.
No, that's DNA, isn't it?
This is the reason we conduct statistical experiments, to see if it is DNA or if it's nutrition, to see the things are correlated, and of course we will be doing that. Yes?
Why are we interested in the process and not in the final result?
Because we don't always have the ability to have the final result. Statistics, thank you for your question. Statistics has two major chapters, let's say. One is description. We will be dealing with that the first half of the course. But the second and most important is inference. Descriptive means I have some data that I have already collected, so past data. And inference means what can I conclude about the future. Now, when you try to assess what will happen in the next national elections, how do you assess that?
You take a descriptive.
Based on the
No.
based on the data.
You make a sample. The statistics companies that try to say
You do an exit poll.
with an exit poll, no,
Yes,
it's too late.
poll.
Now, today, when was the last poll published in the
Oh, yeah.
newspapers?
With the number.
They're saying, if you were voting today, who would you vote for?
That's a poll, isn't it?
That's a poll. That's a sample. It's called a sample in our terminology. A poll is a special form of a sample. Now, we have to infer what will happen on National Election Day from the sample of the 1,000 people. Why? Because there is no statistical company in Greece, anywhere in the world, that can actually sample the entire population and know what will happen on national elections. You draw conclusions from a relatively small sample, and the question is, how reliable are your conclusions from a sample that is not the entire population? So, here it was in principle conceivable that the alien measures all 480. Unless he does, there is no way he can know with reliability this number, the last one, the one that has not been changing. Okay?
But
So
also,
the question now is, if the alien has only half hour to stay here before he goes back to his planet and reports what he found, he samples only 20 of them, he has to draw some conclusions. He has to make inference. Okay, which is what we will go through again. But I'm showing you the process right now. So when you reset sample and you sample only 10, you try to see what is the chance that with 10 you are near the real value. Okay? And in this case, we see it's not. But if I reset, try again, maybe next time I will get 5, something closer. No, not so much. Maybe the next time I will be like it. Or maybe I will develop some math to see what is a good number of sample to be fairly sure and with what probability.
I want to ask that, is that like something like a percentage?
Yes, it is. Yes, because we're dealing with probabilities. It is the probability that the number that I found with 10 people being sampled, what is the error from the correct value? So it has to do with the probability distribution, actually, as we call it. Or is it some movement? Yeah. So before we leave that, let us finish this animation very quickly again, just to see the red line moving. And these paths can be very different. But eventually, in this case, because we are able to get the entire population, in this case, eventually the red will fall on the green. In this case. It seems to be stuck for a while. Huh?
Yes.
But
It will.
again, it's a question. What is the probability that after 200 of these 500 you are here rather than here? These are again things that could have some numerical answer.
But also if we take the biggest and the lowest, we can also be very close to the final result.
If we find the biggest, the tallest, and the shortest. If.
But there can be more people with closer to the highest person.
Which is the next thing I would like you to realize from this chart. Look at this chart, please, and see where the dots are placed. What is this dot here? Of whom? Of a person who is 150, 1, 2, 3, 4, 5, 6, 7, 157 and a half. Who is here 157 and a half? This is the person showing here.
So 8 is logical.
Somewhere here.
Doesn't matter.
It's somewhere here. Okay. And what do we see? What would be the word that you would use to describe the pattern? Yes?
The most are gathered around the average. This way was
Yes, they are gathered more near the average. And some other word that comes to your mind? Density. Very good. The data are more dense here and they are more sparse here. Okay? Density is one of the key terms in what we will study. Now, I showed you two examples until now. We started with Thucydides, the first recorded application of statistical practice. And what did we see? That they applied the averaging, and we saw what averaging means here. That basically, there is a probability 1 out of 480, because 480 here, that the alien happened to encounter the shortest person first. And there is another 1 to the 480 that would encounter this. But generally, as you see, it's more likely that the alien would encounter one of these people here, because there are more of them in this area. But anything can happen. The question is with what probability. Okay. This pattern, where we are more dense around the mean, the average, and less dense as we go far from that, is a very, very common behavior in nature. Very, very common. We will examine it from several sides. It's called the normal distribution. And one of the visualizations of the normal distribution is here, where you see that data are more packed in this area and less packed as they go to the extreme values. Okay. Right. Right. Let's go now to the problem that we discussed last time. Some of you were not convinced that when I tell you that this is a die like the one used in backgammon, you were not convinced that I am not cheating. Huh? You were not sure that I have not made this so that it shows a 6 more often, for example, than the 1. And then we had played with it. But I also asked you to examine what happens when I examine one die, a second die, and their sum. At this point, the technology we are using, you can press, before you do anything else, you can press F9. The function button F9 will every time generate a new phenomenon.
Wow.
Oops. Okay, well, F9 for some reason is not working right now. It's okay, but we can still do our job. So we can still collect in a very similar manner like the last one. So when we click collect 1, what happens basically is like we simulate throwing the dice. Die 1, die 2, and the sum. And whatever happened, we store it. Once more. If you realize the values that appear here are the ones that will be stored here, right? So right now it says 1, 2, and the 3. And when I click collect 1, the 1, 2, 3 is going to be stored. Okay. Now, our task is to see whether the dice are indeed fair. In several of the problems I'm going to give you, you will approach with suspicion. That's good. You will say, he claims that it's a fair die. Is it really? You will try to prove me wrong. Or you will try to verify it. Okay. Whether I did indeed make the formula behave as the real world thing. How will we know that? I remember also last time I told you that if we examine the values appearing here, in either of the two yellow ones, and the one in the gray, you will see that here, more or less, we expect to have every value appearing in similar number of times. The 1 is as likely to appear as the 2, as the 3, as the 4. But the number 7 here is the most likely to appear. And we can see that by collecting 10 right now and quickly examining the values.
This has to do with the combinations of the dice.
It has to do with the combination of the
What
dice.
combinations make 7 round?
Exactly. Exactly. If we examine here, we have the 7 coming of a 5 and a 2. We have the 7 coming from a 4 and a 3. It's harder to get 11. To get 11, you need a 6 and a 5 or a 5 and a 6, so that's it. The other very important thing to note here is that these two, that's a very fundamental keyword, these two events are independent. So what comes in the first die does not affect what will come in the second die. That's very important because we will study this in terms of probabilities. It's important to know when two events are related and when not. This event is a random event in the sense that it comes from random events, but it's no longer independent. It is dependent on these two. But neither of the two is dependent on the other. This is dependent on both. Yes?
Look at this.
We have an improbable event here.
What?
2, 1, 2, 1, 5, 2, 5, 2.
Yes, that's also improbable. Everything is possible. The question is how probable is it? Okay. If we go to the other section, the other sheet, we can actually do some simulation now and collect and see how the visualizations appear. So right now we are conducting the same experiment. What I have here is the frequency of appearance of the 6 numbers in the first die. Here the frequency of the numbers of appearance of the second die. And here the appearance of the sum. Collect 1. Okay, so see what's happening now. It happened that the first one is a 2. It happened that the second one is a 1. Okay. Therefore, their sum is 3. And we see the 3 here. Okay, one more. Now, in the first die, the number 1 and the number 2 appear once each. In the second die, the number 1 appears the first time and for the second time. And here is the 3 and the 5.
Here we got the same. Here we got the same. One
That can also happen. Okay, now I want you to understand this chart. It's a second 2. So this second dot goes on top. Okay, is everybody okay with that visualization?
Yes.
So clearly now, what does it mean if this is getting taller? What does it mean if this becomes taller? More 2's are appearing. So if this becomes taller than all the other bars, what should I conclude?
You are aiming.
And Thucydides is cheating.
Yes.
Yes, he's. Alright, let's see if this will happen. Reset,
Έβαλα 1000.
collected.
Θα τελειώσει το χρόνο.
Sir,
Yes, somebody saying me? Yes.
how can you find a pattern behind randomness? I mean, if this is, okay, we have a result here, the sum from die 1 and die 2, but if we do it again, it doesn't necessarily mean that we will have the same pattern.
No, it will not.
So what are we trying to get?
What are you trying to get? Click, collect, 100. What you're trying to get is the probability of every one of the possible outcomes. What are the possible outcomes of this system? This random system. What are the possible outcomes? The numbers 1 until 6. You don't know what will come next. Will you bet in one of these? Will you bet that the next one will be 4?
No.
If I give you, if you give me $1 on the assumption that you will get a 4, and I tell you if it's a 4, I give you $5 back. Will you bet?
Yes.
Hmm?
Why not?
Yes.
Nice sounds.
The independent events.
I have respect.
No, they're not independent events.
The first
You
time,
bet. You tell me I'm giving you $1,
15.
and I'm betting that it's going to be a 4.
the second
And I
time.
tell you, yes, if it's a 4, I'll give you back $5. Will you play this game?
I have 1 over 6 probability of taking.
I have 5, 6 probably.
No.
These are also things we will discuss.
1 in 36, 1 over 36.
No, I'm thinking about one die.
1 die.
Mm.
1 over 6.
We need more.
Huh.
It depends.
Reset and collect 100 again. Are you suspecting I'm cheating?
Yes.
Yes, seriously, eh?
I trust.
So what do you think I made the second die do? Did I make it give mostly 5s, then give me 1s and 4s, and then very rarely give me 3 and 6s?
Mine is almost linear.
Try it again.
I don't know.
Unfortunately, this is the end of the class,
I say you don't.
so we'll have to conclude next time. Yeah, the problem is I had to make it run with 1,000, we need to change the scale of the charts. So if you want to do this very quickly, let's do this now quickly. Double click the numbers here, make them maximum be fixed to 250. And then also make it change every 50. And then do an F4 here. Well, the same thing.
I need that.
So 250 and 50. It's okay, we will teach these things later. And then again, here this should work with F4. It doesn't.
That's what
250 and 50 and 50. Close, reset, collect 1,000. It's going to take some time. For some reason it's going a little bit slow. But we'll see some patterns now emerging. Yes?
in high numbers, that was high,
You mean
a big amount of songs.
In a large sample size is your question, yes? No, what balances in the middle is when you sum them, but obviously I didn't have the time to complete that today. So today we started our intuitive travel into the world of averaging and what it implies, and we will continue it next class, yes? Yeah, but when you run it 1,000 times, and if you run it even more times, you will see that eventually the inequality will become smaller, the big picture will appear. After that, you run it 1,000 times, your doubt whether I am cheating or not should become smaller. And if you write it 10,000 times, then you will be sure that I'm not cheating. Okay, but when the sums are smaller, you have every reason to believe that I am cheating. Okay, that's for today. Thank you.